What I want to show you is, in today's lab involving the solenoids, we're going to need to get currents that are pretty big. And there's a way to make the meter control the amount of current that's passing through a circuit, not just the amount of voltage. The way you do that is you press these two switches here in, and that causes the power supplies to basically track together. And this one will contribute 1/2 amp, and so will this one. And if I do that and wire it up in this fashion, what I'm able to get, you can watch the current either on here or on here. I like using the meter because it shows me everything at once. I'm going to increase the current. And you can see that's 1/10 of an amp. I'm going to be upping it in tenths, so that's 1/10. There's 2/10, 3/10, 4/10, 1/2 amp, 6/10, 7/10, 8/10, 9/10, and I can get up to just a little bit above an amp here. So that's going to give me a nice range of currents that I can use when making my measurements today with the solenoid. In today's lab with the solenoid, we're going to use a new device that's part of the vernier system. This is called a magnetic field probe. And so what it actually measures is the strength of the magnetic field, which we'll also have talked about in class. And just to show you, you can look at the values here that the instrument records. Remember, the Earth is a magnet, basically. It's like a large bar magnet that has a north pole and a south pole, which means that everywhere around us are magnetic field lines. And they're going to be stronger in some directions than in others. So as I move the magnetic field probe, you can see the value of the magnetic field changing depending on the orientation of the probe in relationship to the magnetic field lines that surround it. What I can do, I can bring a magnet near it. Watch, the numbers are going to get much bigger because magnets like these are much stronger when they're close to this probe than magnetic field is from the Earth. Yes, the Earth's a big, strong magnet, but the magnetic field isn't very concentrated at any point, whereas from this magnet it is very concentrated. And you can see as I bring it closer that the value is going to become significantly either negative or positive. It's all relative to the direction that the probe is aligned relative to the magnet. All right, so you can see how much larger it is there. And then one thing I'm going to do whenever I start to make a measurement is I'm going to zero the probe, so that every time I start, it'll recognize, before I put any current through the solenoid, which we're going to be doing soon, that the magnetic field is 0 there. So anything added on beyond that will be magnetic field caused by the current passing through the solenoid. Okay, I've wired everything up for this lab, and I want to show you what's going on here. I have the power supply wired to the slinky, the plus going to the slinky, and then the negative side of the power supply is wired to the negative side of the meter, and then the positive side of the meter right here is wired to the opposite side of the slinky, or the solenoid coil, which is what this is. So what I'm going to want to do now is count the number of loops per meter that exist in this solenoid coil. So how am I going to do that? It's not just the number of loops, it's the number of loops per meter. And I want to emphasize that that's different, and that is one constant source of confusion on this topic whenever I talk about it. To find the number of loops per meter, one way to do it is to make a slinky a meter long, which this just about is, and then count the loops. And then those number of loops would be the number of loops per meter. Because it's not exactly a meter, this end is kind of bent over, and that end, it's not perfectly spaced right at the end, but everywhere else it's perfectly spaced. I could take a fraction of that meter, let's say 10 centimeters, and count the number of loops in 10 centimeters, multiply that number times 10, because there's 10 10-centimeter segments in a meter, and then that number would be the number of loops in a meter. So I'm going to pick a 10-centimeter length, which I marked off with these two pieces of blue tape here. That's about 10 centimeters. I'll line it up with my slinky without interfering with things here, and I'll count the number of loops. I see 1, 2, 3, 4, 5, 6, 7. About 7, but there's some uncertainty there. Because you might say, well, was that another loop in there or not? The way to minimize the uncertainty is to get a longer segment and count the number of loops at, say, 1/2 of a meter, and then just double it, and that would give me the number of loops per meter. So I'm going to take a length that's 50 centimeters long. I'm going to start here. That's 20 centimeters on this meter, and go to 70. And I'm going to count. You're going to watch me count. So I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 30, I'll go with 34. So 34 loops in a half meter means 68 loops in a meter. So our first slinky coil that we're going to be using is going to have 68 loops per meter. That's its little n. That's going to be used in the formula that we're going to need later. So 68 loops per meter, I'm going to write that down. You should write it down too. Now what I'm going to do is I'm going to zero my sensor, and I'm going to do that in between each measurement, basically. Or, well, actually, I'll probably do it once and then just keep upping the current, knowing that I'm very close to 0 right now. Then I'm going to press collect. And it should be recording something at about 0 milliteslas. Remember, the unit of magnetic field is the Tesla. Millitesla means 1/1000th of a Tesla. And then I'm going to turn on my power supply, and it's at 0.1 amps. And so we should see a little bit higher magnetic field now than we did earlier. 0.1 amps. It's not a lot higher, is it? But I can record that value by taking the average over this region right here, which is about where I turned it on. Hit Analyze and Statistics. Looks like the average is 0.0067, or about 0.007 milliteslas. So it's pretty small, but it's bigger than it was. I'm going to take the beginning to be 0, then this I'm going to take to be 0.007. Let's see what happens as I get it bigger. So now I'm going to go to, and I'll press collect again. I'm going to go to 0.2 amps. I'll get out of the way in a moment. There we go. Very close to 0.2 amps. And we can see that the magnetic field is now bigger than it had been. So let's see what we got here. This region here is all a region where I had upped the magnetic field to, well, actually, I'm going to press collect again because now I know it's at 0.2 amps. And let's see what it's at right now. Okay, I'll press stop. And I'll do the statistics on this data right here. Analyze, statistics. And we're at 0.02. So I was at 0.007. I'm going to write down these data too. 0.007 and now 0.02 milliteslas. So it's getting bigger. Now I'm going to move this up to 0.3. There we go. 0.3 amps. I'm going to press collect. Shall zero it. No, I won't zero it. That was dumb. Got to turn this off now. And I got to zero it again. I shouldn't have zeroed it with the power on. Okay. Now I'll turn it back on. Now it's at 0.028 milliteslas. So it's gotten up a little bit. So 0.020 0.028 now. And now I'm going to go to 0.4. Pretty close to 0.4. I'm not going to press 0. I'm just going to press collect. Now it looks like I'm at 0.038. It's definitely going up. All right, I am going to up it to 0.5. There we go, 0.5 amps, really close to it. Press collect. The mean is 0.048 now, 0.048, or actually 0.049. 0.049. Going to up it again, 0.6 amps. There we go, 0.6 amps. Press collect. Let go for a few seconds, stop, and now it's 0.057. Okay, I'm going to up it to 0.7. Press collect. It's getting bigger, as you would expect it would, because a bigger current means a stronger magnetic field in the solenoid. The mean in there is 0.070. Getting there. I'm going to go to 0.8. .080. Going to 0.9. .9, I have 0.089. Now I go to 1 amp. This is going to be my last measurement with this coil spacing. As close to 1 amp as I can. It's pretty darn close. It's actually dead on. And the mean I have now is 0.097.